Okay, it's 2:30, so welcome to this session. Thank you for coming in after lunch. We'll try and keep you nicely awake. So we've got 4 interesting papers about fingers and technology. So first up is Ian Oakley, who's going to talk about the flat finger, and I will let him explain more.
Okay, so thank you for the introduction. I'm Ian. This is work, the flat finger, I did with my students and interns in summer 2015. So I worked with Carina, Katie, DoYoung, and Rasel. As you can probably tell from the pictures on the right, this is a talk about smartwatches, or maybe what I'm going to call a YAST, or yet another smartwatch talk, because really there's been an awful lot of them this high. And for example, I saw on the first day, Gupta et al. Showed Joule Tap, I think, where they used finger disambiguation to facilitate typing on a smartwatch. Earlier this morning, we had an elicitation study of input on smartwatches, looking at what gestures over the surface of a smartwatch would be maybe able to inform input. And later today, we have an exploration of how we might be able to use multiple fingers to select commands more rapidly. That's in the next session. Actually, I forget all these paper titles. But this is all representative of the kind of smartwatch input we're seeing today. And so why is there a sudden uptick? Well, partly it's obviously the availability of the devices, but it's a little bit more than that. So all this huge amount of interest, I think, is being driven fundamentally by the fact that these are powerful computers. This I didn't do, so you're probably not going to think I'm insane, but this is someone who's installed Windows 95 on an emulator on their smartwatch. Yeah? And so this is really showing that this is a powerful computational tool. You can really, there's a lot of brains in there, there's a lot of memory, there's a lot of connectivity, but what there isn't is any sort of meaningful way to interact. So you can hear this massive finger looming over this Windows 95 operating system. So if you want to see more about how to do this, there's his YouTube link. And also note that the main disadvantage he saw, the main problem he saw, was the emulator was a bit slow because he couldn't set the memory up correctly. So, I mean, I think there may be strange people out there. But what we've got basically is very powerful computers. I mean, as powerful as computers bigger 20 years ago, the desktops. We have them in these tiny, tiny packages. We really have almost no way to get that power. I think this is one of the fundamental limitations of the device, and unless we can resolve these kind of issues, they're going to fail to live up to their potential. So all this work at Khanh is trying to look at ways we can interact with smartwatches in richer fashions. And fundamentally, one of the reasons the way we interact is very sparse or reduced is that we focus predominantly on touchscreen interactions that are being popularized in much larger platforms. So here we're talking about things like tablets, phones, the big smartphones, even the tabletop computers, and their reliance on the standard touchscreen technique of selecting things or maybe moving around or swiping. And these work well on really large devices, but on a smartwatch, you don't have that much space to have a lot of options to select. You don't have that much space to move very much. And so these really fail to scale in a sort of rich or expressive way down to these very, very tiny sizes. And so many of the papers I showed briefly at the start, they're trying to sort of create richer types of touch that are tailored to the smartwatch experience. And that's also what we do. So the particular thing we're going to talk about in this paper is how we might be able to use the contact area of a touch as a way of mediating or facilitating that input. So a typical touch on a smartwatch is just with the tip of a finger, and we resolve it as a point. So you touch a point, and that may be used to select a target that's under that point. We're saying that actually with our fingers and the size of the smartwatch, we can actually make different shapes or forms on the surface of that smartwatch and use the contact area of that touch as a way to mediate or control or as a parameter to the input. So here on the right, I have a finger laid flat, the flat finger, on the surface of a smartwatch, which is leading to an elliptical touch region. So we're going to explore the value of those elliptical touch regions. I should nod before I go on that this is not a fully new idea. In fact, the touch regions have been studied by a number of authors in a number of venues. You probably cannot read the venues. But here I have on the right 2 examples from tabletop computers, Shape Touch from Tabletop 2008 and Rock and Rails from Khanh 2011, which worked on tabletop computers and explored hand shapes. So these are shapes such as lines or angles or actually just whole finger profiles on large computers and how we might use those to, in Rock and Rails, for example, to manipulate objects, make translations and scales and so forth. So this is looking at big shapes. On mobiles, people have also looked at this. The fat thumb, mobile HCI 12, or work on detecting and leveraging finger orientation in WISTO 9 is all looking about how we might get some value out of what's happening to fingers on phones in order to do things like mode switching, the fat thumb, for example, switched modes depending on the size of the contact region. So you could do 2 different operations. And when they were detecting finger orientation, they proposed things like pie menus that you could twist around to make selections. So these kind of topics have been explored. What we're really doing here is saying some of this work may not apply to this very constrained smartwatch paradigm, where we have the screen strapped to one wrist. Maybe our thumb is not the best interactor. Maybe we have like other constraints in terms of angle, other types of shape we can make. It's just sort of exploring this issue, revisiting this issue in the context of the smartwatch. So basically we came into this with several questions. One is we were curious, what forms of area touch can we make on this tiny form factor? What can we produce? What kind of thing is viable? What kind of thing fits the human body? How well can we do these? And then if we can make some of these things well, how could we actually use them to design interactions? So what kind of input can we do? If we're not selecting things, what could we do on smartwatches instead? How could we put these meaningfully on the watches? Okay, so to answer these questions, the first thing we did is build this rather preposterous piece of hardware. And so this sort of looks like a kind of a long, skinny watch with a little unit on top. I'm going to explain what it is in a minute, but first I'll tell you why we bothered to build it. You may be asking, why do we use a watch? But in this work, we thought we wanted to use something which is a watch form factor. So it's really important when we're going to cover the device that we have physical cues from its edge. So if we're going to put our fingers on it, we're going to obscure large portions of the screen, and we want to be able to feel something that's like a watch. So this precluded us from using a phone. So a lot of previous smartwatch work done in Khanh has just slapped the phone on your wrist, and you sort of touch the phone because it's easy to program and so forth. But that's not going to work for us because we want to have the physical affordances. We also wanted to minimize the bevel size for the same reason. So we wanted to be able to touch right to the rim of the device and sense those touches because we felt the physical feedback from the edges would be very important. And many smartwatches, like my one for example, have a raised bevel, or an Apple Watch has a large bevel of 6 millimeters, and we thought that this may impact the kind of data we'd be able to get. And so we thought maybe this is not suitable. And then finally, we are really not certain what we get from touch APIs on these kind of watches. So a lot of them have palm or pocket rejection, these kind of algorithms which are filtering the touches, because we're interested in what touches people can make, not what touches I get from the OS. We thought actually it's maybe better to make our own sensor. When we were making it, we regretted that. But that's the decision we made. So the final thing we produced, so there's a sensor unit in the center of this little white box, which extends along the wrist. It's a 33 millimeter square, 3 millimeter raised, so it has really distinct edges you can sense. On top of it is it's basically smartwatch sized. On top of it, it's a 7x7 grid of capacitive sensors. Each is 3 millimeters in diameter. Spacing is 4.5. This is typical of a touch screen. The spacing is around 4 millimeters usually where a sensor point. We got the bevel down to 1.5 millimeters, so it really extends right up to the edge. We can sense any touch to the surface, pretty much. It's all connected to an Arduino. There's a sort of big box around it with all the bits in it. And eventually we got a 40 hertz sample rate, so we can get things relatively fast out of this. And we also capture proportional changes in capacitance. So each of the sensors has a baseline, and we touch it, this alters, and we get the proportional change, which means we can interpolate between the touch sensors. So we can give you sub-sensor resolution, like a regular touch screen. So sort of we re-engineered a silly touch screen because we wanted some very specific properties. Now this is the kind of data we get. So you can put your finger on this in different orientations or different numbers of fingers, and we get these sort of contrast map, heat map, which will highlight the touch points. So in order to process this as area touches, we obviously need to do some work. We can't just use the raw data. So we fit ellipses. That's a pretty standard process. And then we need to just figure out which ellipses to examine if we're going to examine area touches and area touch production. So the first thing to note about this kind of area is that the initial or final touch is not representative. We need to wait a little bit because an initial touch, maybe with a part of a finger, and then it flattens out into a larger touch, or vice versa. So we actually have we just set a small threshold of 75 milliseconds before and after, and we examined the contact and release touches at 75 milliseconds after event. We then performed really simple classification to say something about these ellipses. Basically, we classified the centroid into a 3x3 grid, so left, center, right, top, center, bottom, and then we gave them an angle of horizontal, 40, or vertical. So we have a very basic classification of these kind of ellipses you see here at that kind of resolution. The second ellipse is a top horizontal ellipse. Very simple. Okay, so after we build this thing, what do we do with it? Well, we conduct a study. So first we did a targeting baseline to see if our sensor really works. Is it good enough to run any form of study? So we had participants do that. And then we generated a large set of candidate touches and gave these to participants to perform. In this case, the emphasis was on sort of giving them time to practice and learn how to perform these so we could see if they could make these touches. And after they'd gained some experience, we just tested them on their ability to produce any of the touches in a typical experimental paradigm. Show the touch, they have to make it. We ran this with 20 participants. All feedback was on a PC. You've noticed their device didn't have a screen. So obviously we showed instructions on a computer in front, and they manipulated a device on their wrists. We measured your standard time and errors, but we also looked a little bit about how people touch by capturing how they touched it with their fingers, how they touched the screen. And also we measured their hand size, because we were curious if little people couldn't use it and big people could, or vice versa. Is hand size a factor? So a little bit more about each stage. So to capture our targeting baseline, we just on the screen, we showed instructions like this. So we had a 2x2 and a 3x3 grid of buttons. These are typical arrangements you might get on a smartwatch. When someone, in one of these trials, we showed the black square, and when they touched the watch, we showed the little cursor, drag the cursor over the button, release. So this is basic targeting. The targets were 11.5 and 6.6 millimeters. For the area touch production, we generated, let's say, this large set of possible area touches. So we generated 33 touches. In this production phase, they were delivered to each participant in a random order, but once they were assigned a touch, they did 15 repetitions. So here we're getting them to practice. So that, the first time we show it, they're figuring out. Hopefully by the 5th time, they have a good idea how they're going to make it. By the 15th, they're kind of confident. So we divided these touches into 2 classes, static touches and dynamic touches. Static touches start and finish in the same place. They don't move. They just touch and release. Whereas dynamic touches involve a change in the area that is being touched. So it's static. We had lines, diagonals, and pairs of lines. So our lines were simple things like just placing your finger vertically over the center of the screen, or the left or the right. We had horizontal lines, the top, center, bottom, and then 2 diagonals. Corners, equally just touching the corners in a diagonal. And then pairs of lines were 2 fingers doing the same, vertical, diagonal, horizontal. So say dynamic touches involve movement, and so these movements were translation, rotation, or what we call transition. Movement is just moving from one line to another line. So we might make a horizontal line on the bottom, and then move that horizontal line to the top, one from the left, moving it to the right, diagonal to the bottom left. We had a set of 8 of these. Rotation in informal testing was really hard to do, so we reduced it, and we just actually looked at 2 rotations we felt might be viable. And they were going from the diagonal top left, bottom right line to horizontal, and diagonal top left, bottom right to vertical. So just 2 simple rotations. Our transition points were touching with the finger to flat, or flat to finger. And again, we did that in 3 orientations, from horizontal, diagonal, or vertical, diagonal, and horizontal. And so this led to 15 static touches and 16 dynamic touches. Okay, I want to quickly go through all of this. And then in our test phase, after participants had practiced, we just delivered all these touches in a random order, in several blocks to establish performance with the set. There's a lot more results in the paper. Really just going to touch on them briefly. We separated time into preparation time. So this is after giving an instruction until touching the screen, and touch time, which is touch to release, because we felt these might be different. We say that a few trends. So in our button studies, the preparation time is low. You just touch the screen, but the touch time is a little bit up. And in our area touches, it's the inverse. So it's more preparation. How should you orientate your hand? What does this trial mean? Work on this. But the touch time is very short, because you're actually not doing a lot of work with the device afterwards. On average, our times are 1 second to 1.2 seconds. This is kind of typical of smartwatch performance. So the area touches are relatively equivalent to target work. So I think this is kind of positive. Error rates for our buttons are also typical with the literature. Our small and large buttons, 6 to 10% is typical. Area touches are a little bit higher. We see a strong practice effect. And then the purple bar on the right is the performance in the test. This is a more complicated scenario at the end, but it's actually lower error rate, suggesting people are showing significant improvements, and probably we didn't bottom that out. Pulling a few more things out of this, we see a big temporal distinction between our static touches and dynamic touches. So our static touches, which don't involve movement, are fast. They're just touch and release. There's no targeting or adjustment. So they were 400 milliseconds, and probably they could be faster with more practice. But people are really quick at this, suggesting it may be useful for all sorts of shortcuts or rapid access. Dynamic touches were more slow, more like a normal targeting operation, but not really slower than that. We have the error rate in detail in the paper. I'm not going to dwell here. Just going to say that it was a huge range of different error rates. We didn't focus on this in our work. The classifier was if statement classifier. There's no work on classifying this input. There's no work to reduce this input. There's no real processing of the sensor data. So we feel that what we're trying to do is describe people's successful performance, and their error rates is something that we need to tackle in future work. We have a long discussion of error rate in the paper. But obviously, I think it is indicative of what's easier and harder. We cannot ignore it. But we don't really feel that we've actually tackled that issue. So some were easy, some were harder, but the default point is not clear. Maybe more positively, what we saw was very minimal classification of area touches as target selections in either the 2x2 grid or 3x3 grid. This means that because our area touches involve long strokes, if we said that long strokes cannot select targets, basically there's no overlap between this and target selections. This means that we can use this kind of touch alongside traditional input techniques, like without disrupting taps and strokes and swipes and so forth that we normally use. This is kind of a plus. We also did regression. Hand size has no impact. So small people can rejoice. Big people can rejoice. People also used a wide variety of finger postures, which you think is positive, as many of the touches we proposed are sort of easier done with different fingers or different orientations of your fingers. So 2/3 were flat, using the finger pad, and then they would also use the sides of their fingers if that was more appropriate. People also use different fingers. Again, index is predominant, but people use the ring, middle, and thumb. Some of the gestures are really much simpler like that. A touch to the top of the watch is much, much easier with your thumb than it is with your finger, which involves sort of pulling out your elbow. And we were kind of curious if people would figure this kind of thing out. And some did, some didn't, but there was a trend towards that. Two-finger touches were pretty obviously all index and middle. These are the only two fingers that are really well positioned. So sort of basically encouraged by this, we also wanted to tackle our second question, so feeling that we have a reasonable time, error, and usability performance. How would we integrate these things into design of interfaces for smartwatches? So we did two things. The first thing we did was a workshop with 5 academic designers. This workshop basically had them sit there in a structured brainstorm, come up with different interaction techniques for this paradigm. And the second thing we did was take the results from that workshop, plus the results of our study, and then we got a silly little projector, down projecting on our DAFT sensor, and actually had a little interactive screen on top of the whole thing. So we built some demos with this, and then showed them to some people to get some initial feedback. So here you can see the little projection of a UI onto this sensor. So we could actually get something that's a fully interactive, although pretty restricted. People are stuck to the table and so forth. So I'm going to just briefly talk about some of those interactions, mainly along 4 themes that emerged from the design workshop. So the first theme was, and one that recurred frequently, was that the touch patterns, the area touches, were really, really useful as shortcuts. So they didn't really seem to have to relate to on-screen content. So a really quick way to just get something you wanted. Like pressing a button on your device may pull up a menu. Touching it in a certain way may be used to just pull up a function. So here's a general example of this, where 3 touches might be used to call up 3 shortcuts, or a specific example that came from the workshop, where you would silence or turn off your phone by making a specific pattern. So we integrated these into our demos. These pictures, they're pretty clear. Integrated these in our demos in a few ways. So one, this is just 2 examples. One is when you lay a finger horizontally along the bottom of the watch, we popped up a little menu. And then you could tap. So the menu showed some little buttons, and you could release and just tap the buttons. The second one was we called a glance window. You could lay a finger alongside the watch. A window would come in, maybe showing a to-do list in this case, or a calendar. When you released it, would pop back. So you'd just be able to access a second screen with just a single touch. Second thing our designers came up with was the use that some of these shapes are they have analogy to real things, and we could use that as a way to cue memory. So in this case, inspired by the checking a pulse with 2 fingers, thought that laying 2 fingers on the watch would be able to trigger a health app or a heart rate monitor. Another example was making a cross to make an emergency signal. So make a cross on the phone to issue this command. We put this in our little demos. In the concept of a media player, we used a single stroke across the device to be a mute, like laying a finger on the lips, and then 2 fingers across the device as resembling the pause icon, which is 2 bars, so play pause. So mute, unmute, and play pause. Our designers also thought that our touches may resemble actions. So one that was very commonly cropped up was the idea that we could transition from a line to a point. It's like picking something, or a point to a line is like putting something. And so there were several examples where this would be used for those kind of operations. The example here is copying by going from flat to point, and pasting by going from point to flat. Another one we put in the demos is coverages deletion, or coverages hiding. So if some content you don't want it, you cover it, and it disappears. You cover it, and it is deleted. Our final metaphor was a spatial metaphor, so there's a whole raft of these. And so a lot of the moving touches, they seem to have some sort of, they have a strong spatial component, so people thought you could push stuff to another device, or save stuff by moving towards yourself, or zoom in by moving clockwise around your arm, zoom out by moving anti-clockwise. So there was a whole bunch of this. This is kind of similar to how we might think of using swipes today, so maybe a little bit less rich than the others. As I say, we showed these to people. I don't have time to dwell on this. I've already been waved. Yeah. So I'm just going to say that generally people like these. They thought they were quick, easy, and accessible. They were designed to be those kind of things, so it's kind of positive. They also felt that they were memorable, particularly in terms of those that had iconic relationships, like the pausing or the muting or the pausing, because there is some icon they could relate to. They were concerned they were hard to discover, like many of these things. There's nothing on the screen, so it can be hard to discover. And there were some concerns at the start of the study that this kind of touch would be awkward, but as they grew a little bit familiar, this faded. So in general, we think there's some potential, both in terms of human performance and in terms of sort of directions for design that might be valuable. Obviously, lots of limitations. We didn't use a real watch. We regretted that at the end, but I think we got some value out of using our hardware. Our recognizer is very primitive, obviously needs to be improved, and obviously there are other device shapes, such as round watches, and what we found out may not apply to those, so we should think about those in a little more detail. This is my talk, so thank you.
Hello, thank you for the talk. My question is, you showed a lot of new ways to interact with the watch. So how long does it take for a user to learn the new way to interact with it?
Yeah, so I mean, we didn't show any like a unified vision for interaction, and so answering that question would be hard. So if we set up some metaphors, like for example, because I have a metaphor like a line across the right always meant move right, like a swipe to the left means move left. But we didn't set up those kind of metaphors, so learning is it's impossible to answer that question, I feel, because we looked at individual instances rather than any general framework. Users were concerned it would be hard to discover, but in most part they were not concerned it would be hard to remember. So maybe this says that there's some hope. But yeah, we didn't really manage to address that concern.
Okay, thanks.